All right, guys, so just a couple of things to review. We said that eugenol has a benzene ring. Stay away from it if you're working with benzene as its own. But when benzene gets involved in a structure, the properties completely change. So, no worries. We can swig this stuff in our mouth and spit it out and not have a problem. And we said that eugenol ends in a OL, and the OL means alcohol. So this OH group is going to be your alcohol functional group. I know that I keep saying that over and over and over, but I want you to be prepared for some of this stuff if you've not taken organic chemistry yet, and you're required to take organic chemistry at some point in time. So that's the alcohol functional group. We also have another group that's pointed up here to the top, and this is a OCH3 group. And I write my CH3 groups that way. On the previous slide in the previous video, you've basically seen it OCH3 written a little backward, but it's the same thing. No matter if the carbon is written first or the hydrogen, it basically means the same thing. So that also is a functional group, and that functional group, the way that it's written, is a R group that has an oxygen and another R group after it. And whenever we see that formation happen in a laboratory or in chemistry in particular, we're going to call this a ether. So this is an ether group that's located on the eugenol. So again, just another functional group. This is a name, a general name that's given to that particular type of template, and that ROR is representative of an ether. And then over here to the side, we said that there's 3 carbons, 1, 2, and 3. So I can draw the dots there if it helps you visualize that a little bit. There's my 3 carbons. And we said that was propene. Propene, as far as the category that this is classified as. The ENE ending, we said, stood for alkene, and an alkene basically means a double bond. So in this particular structure, the double bond is going to be located right there at the very end. So that's the structure for eugenol. Now, we talked about the pKa of this in the previous slide, and we said the pKa is 10.19. And you're probably wondering, well, what the heck is pKa? I don't know what pKa is. Well, that's for the purpose of this video. That's the purpose of me, to teach you something. So let's talk about what pKa is. So in the beginning, when we first start talking about acids and when we start talking about bases, and if you've taken other courses from me before, that's the same deal. There's no difference at all. We've incorporated and introduced an acid and a base. So let's say that we have an acid like HCl, and that HCl is basically going to break apart into H plus and Cl minus, because HCl is a strong acid, right? And we said the definition of a strong acid is an acid that gives off all of its proton. And proton is simply a hydrogen here. So that means if I take HCl and I dump it into an environment like water that can make it break up, it's going to fully break up. None of it sticks together at all. All the H is going to be released, and all the Cl is going to be released, and they stay away from each other. They might come together in a brief moment in time, but then they're going to break away again, and they're going to stay free in the solution. And we call that strong acid. So any strong acid will behave that way. But we also have weak acids, right? And a weak acid is basically another acid that doesn't quite give off all of the hydrogen. So that means a little bit of it will go forward, but some of it will stay behind. And that's kind of representative of what we do in a general chemistry course when we write those arrows like that. That means that it's not going to go to full completion. What will happen is that the CH3COO will come off, and some of the H plus will come off, but not all of it. and that's a weak acid. Not all of the proton gets released, okay? And acetic acid, which is basically vinegar, is one of those weak acids. So the question here is, when on Earth will this hydrogen basically be spit out, right? When will the molecule decide to release that proton and release as much of it as it can and completely break away from it? And that's what the pKa value represents. That pKa value means basically the pH at which the molecule releases the hydrogen. Okay? So let's say that CH3COOH has a pKa of 4.2 or 4.3, whatever makes you happy. I don't care. We're just going to make up a number here. What does that represent? Well, pKa, the A stands for acid, and the K basically stands for a dissociation constant. Yeah, that's a mouthful. Dissociation constant. It tells me basically a little bit about equilibrium, which is too much detail to introduce here, and when the molecule will spit off that hydrogen when it comes to equilibrium. And P represents anything just like pH does. It's just a value that's a logarithmic value. And again, we'll talk more about that in a later video at a later date. So what does pKa mean to me? That means that if I take this molecule and I dunk it down into some water or some solvent, and let's say that the pH of that solution is a 2, then that means this molecule will stay together. It's not going to dissociate. It's not going to break apart. So CH3COOH. That's the way it went in. That's the way it stays together. So let's say I put it in another beaker, and let's say that I change the pH of it, and that pH goes to 4. Well, the pKa is a 4.2 in this example, and that 4.2 or 4.4 or 4.6, whatever it is, I don't really care, but that value is still greater than 4. So that means that this molecule will still stay together and it will not break apart. The pH of the solution has not went over the pKa value. So nothing is happening to my molecule. It's kind of like a savings account. Think of it that way. Your savings account this month, you didn't need to tap into it. You didn't spend that much. Well, the next month, you didn't tap into it either. You didn't spend that much. But let's say the following month, well, you get some flat tires on your car because you made somebody mad one weekend on a Friday or Saturday night downtown, and they're going to come by and they're going to slash your tires. Well, the savings account has to be dipped into, right? And let's say that in my third container, my pH now is an 8. I increase the pH, which basically means I've made it more basic, right? pH over 7 is a base. The molecule realizes that now. And the molecule says, oh, whoa, wait a minute here. You're putting me into an environment that's a base, and I'm an acid because I have a pKa value, and I'm basically telling you what pH I will give off my hydrogen. And in this case, my pKa is lower than the pH of the solution. And because of that, this molecule is going to break up, and it's going to kind of help out the system a little bit. And it's going to try to donate that proton to solution so that way it will lower the pH down a little bit. It's trying to do its job, is basically what I'm trying to say. The savings account is trying to help you out. And that molecule realizes that you're in trouble because you're in a basic environment. It gives off some hydrogen to kind of help out, bringing it back down to neutral or back to the acidic environment again, and all of the H's begin to pop off of this molecule. So that's what pKa represents. So make sure that you're familiar with that term, because this is a term that actually shows up very often in the laboratory. pKa's, they're very important because it tells us what the molecule's doing on a chemical structural level. Now, the other thing that we talked about in the previous video is this whole concept of boiling point. And we said that the boiling point for eugenol is 254 degrees. Now, we're going to have a problem, because that means that if I take a flask and I basically fill that flask full of water with my clove buds on the inside, and I heat this water up, the issue here is that water will boil at 100 degrees, right? If this is water, it will boil at 100 degrees, and when it goes over 100, it begins to evaporate. And if I've got this thing on a distillation, and I'll show you a picture of that in a minute, but this water vapor is going to come over here, condense back down, and it's going to go into a receiving flask that's going to slowly get filled up with a solution. Well, if I only do this and that's it, I can only go to 100 degrees. That's it. And the problem is that eugenol is at 254. And I am way, way, way below eugenol's boiling point. So what I would end up with over here in this receiving flask is basically just water. And that's not what I want. I want clove oil over here. So the issue is, how on earth do I get the clove oil, which heats at 254 degrees, to go over to the other side? Well, the first choice that most people would pick would be, oh, well, choose a different solvent. Choose something like an organic that has a higher boiling point. Well, you could. The problem, though, is that organics typically are very explosive and flammable. And I don't really want to use organics in a distillation setup if I can prevent it from happening, because that's a hazard that I have to deal with. So that is a plausible option. You could choose a different solvent, and that solvent, make sure that has a higher boiling point, closer to the eugenol boiling point, and maybe you can really crank the heat into this stuff and really get it to go over. The problem, though, is that there's actually an easier way to do it. And number two is to use water, but this time use steam, because steam is actually hotter than boiling water, or the soup of boiling water that you've got. So very often what you would do is that in a lab you would have this boiling flask, and here are your clove buds, and there's a little bit of water. So water and clove is going to go here, and you're going to heat this guy up. And this is going to make this stuff hot, right? And at 100 degrees, that water is going to start evaporating off. However, if you take another container and you fill this full of water and you heat this one as well, well, this is going to generate some water vapor or steam, and that is going to be directed over into this flask, and that is going to create a much hotter environment. So think about that for a minute. You're boiling spaghetti water on the stove, and you put your face over the water vapor that's leaving. It's going to be super hot, and you can scald yourself if you do that. The same concept is happening here. That is very hot steam that's coming off from that water container, and this steam is about 212. That's typically where this begins to start, and it can get even hotter. So that, with the addition of the hot water and the clove in a slightly pressurized system, is going to make the eugenol now, and I'm going to draw that in purple, the eugenol is going to get evaporated or volatilized, and that vapor is going to turn back into a liquid, and you will collect that oil over here in the receiving flask. Now, the problem is that that oil is also going to be mixed with a little bit of water. Okay, so water is going to come over as well as your oil, and you're going to have more water than you will have oil. I'll just go ahead and tell you that. It's no secret. You're going to have more water in the flask, in the collection side, more than you will the oil. So how do you know when you're done? Right? That's often the question that people have. Well, the distillation will stop when you start seeing drops over here on this side that are not cloudy anymore. If you see cloudiness, that means your oil and your water doesn't mix. And that means both of those are still coming over. But as soon as you see clear droplets, that means only water now is coming over into your collection flask. And that water is not carrying any more oil, which is a very good sign that all of the oil has been distilled from your clove oil that you have weighed out. So that is why a regular distillation will not work in this case. You need hotter temperatures, and that hotter temperature has to come from a steam source, which will increase the temperatures of the clove oil, and that will make the eugenol volatilize and turn into a vapor and go up and over your distillation setup. Okay? So hopefully that seems to be okay with you. Here in this slide or this picture, this is what your normal steam distillation will look like. So here in this flask, we've just got water. We're going to heat that sucker up, and that vapor is going to come over into this middle boiling flask, and that middle boiling flask is going to have your clove and some extra water, and that's going to be heated as well, and that eugenol is going to turn into a vapor, and then it kind of goes over to this side where the condenser is at, and that condenses it back down into a liquid, and you'll have a receiving or collection container over here. So you'll be getting the water and you'll be getting the clove oil both. Here's a different type of setup that's still a steam distillation. Here at the very top, this is going to be water. That is a water source that you can keep basically replenishing that water and steam into this main boiling flask. And here's just an elbow, and that elbow is just connecting it to the condenser over here to the side, and then that will go into a receiving flask over here to the right hand. This is a vacuum adapter, and the reason that you're seeing a little nozzle on this elbow is because that could be hooked up to an aspirator, like you're going to hook up a Buckner funnel to an aspirator, and that can help pull things and pressurize things to make the distillation a little bit quicker. And then finally, here's another steam distillation setup. So we see a separatory funnel that's used here again, and that has some water source. You're going to heat this solution up in the 3-neck boiling flask, and that water is going to be hit with some steam. The water gets hotter. The steam makes the eugenol vaporize and evaporate and go up. This is a connecting neck and the sidearm neck, and that goes into a condenser, which then goes back down into a receiving flask, and they've used an ice water or ice bath over here. So same type of setup, no difference at all. If you want to extract essential oils at home, you can do this. You can set up your own steam distillation, and the way that you would do it is that you would take a pressure cooker. So the pressure cooker is going to cook things at a higher temperature. That's why things cook faster in a pressure cooker and why people use them. So inside of this would be your clove bud and then some water. You're going to So over in the white bucket, this is where they basically would keep some ice. And this is a circulating coil that will go through those really cold temperatures, and that will condense and recirculate the vapors that basically go into this coil and cool back down, which will be collected into the collection jar over on the right-hand side. So this is your homemade version of a steam distillation, and it will probably actually be a little bit easier to set up and probably work a little bit better than the setup that we're going to be using in the lab. So keep that in mind. You can home make these things if you need to, and if you want to extract your own essential oils at your home. Here on the next slide, you're going to see pictures of what real steam distillation looks like in an industry environment. These are much bigger, these are larger, they're more mechanical, but the same concept is basically here into these pictures. So you're seeing a pressure cooker that's here to the left-hand side. That's where your sample would go with a little bit of your solvent. This would cook at a very high pressure. The fumes would go up through the tubing and into the condenser that's over here to the right-hand side, and that condenses down into a collection jar that you're seeing. It's kind of stainless steel that's a little bit hidden behind some of the tubing out here in front. And then over here to the right-hand side, you can see that these things can become much larger depending on what the product is and what the manufacturer is, where the collection jars are basically going to be way up here at the top, and you're going to have to take a ladder in order to get those essential oils or whatever is distilled from the steam distillation setup. So that's kind of how this translates to industry. That is what the regulated type of mechanical parts would look like at a company if you are blessed to work in one of those. Okay, finally, the lab scenario here. A batch of clove oil looks different, and as a part of quality control, the oil needs to be tested against pure clove oil. So you need to extract clove oil from cloves using steam distillation. After the extraction, you need to confirm that it is the oil using infrared spectra. So you're going to run your product and you're going to run the pure product, and you're going to compare those two images with each other to see if they're similar, and the SDBS of eugenol, and compare it to your product as well. So SDBS is a link in Blackboard spectral database system. It will direct you there, and if you've not used SDBS before, you need to come and let one of us know, and we will guide you in the right direction. The extraction yield should be greater than 75% of the expected. So we know that you're going to lose a lot of product here. We know that the clove oil can be quite stubborn to obtain, and because of that, we're lowering the percent yield down to a reasonable 75% yield. So good luck with the lab. I think that you'll smell good. I think that you'll make the lab smell good. I think that you'll enjoy it. And you can even do these processes at home if you've got other things that you would like to extract essential oils from. You just need a pressure cooker.